And SCR is mainly used in relay control, phase control, motor control, heater control. See, all the control applications I'm going to use SCR because I'm having a gate terminal, right? So this gate terminal is going to control the operation of SCR. So wherever I need to turn on the SCR, I'll be using in those applications. I'll be using SCR, battery chargers, inverters, RPS, and static switches. So if you want to explain the operation of SCR, I can explain the operation of SCR by considering it as two transistors. It is called as two transistor version of SCR. So see here, SCR is a four terminal device, PN, right? So I can consider it to be made up of two transistors. See here, P1, N1, P2. N1, P2, it consists of one PNP and one NPN transistors. And these two layers are joined. So this P1 and N2 will be in full, and N1 and P1 are same, P2 and P2 are same. So I can, if you split this, you get one PNP transistor and one NPN transistor. So see here, so I have one PNP. When the arrow mark is inside, you know it is one PNP transistor, and when the arrow mark is outside, it is going to be one NPN transistor. So whatever coming out of N2 is cathode, whatever going into N1, P1 is anode, and gate is present in P2. P2 is going to be the base. So you see here, this collector and base are joined. A base and collector are joined. So see here, the collector of PNP is joined to the base of NPN, and the collector of NPN is joined to the base of PNP. So this is from this diagram. Okay, emitter and emitter are separate, and the bases or base and collector of NPN and PNP are shorted. And the terminals you have to mark: P1 it is going to be anode, and N2 it is going to be cathode, and P2 it is going to be gate. And you see here, you mark the IE1, IB1 and IC1, the emitter current, collector current and base current. Same way for IB2, IC2 and IE2, IK and IA. IK is cathode current and IA is anode current, IG is the gate current. So we have marked all the currents. Now we are going to split the SCR into two parts, displayed mechanically from one another but connected electrically. So even though we have split this, but logically everything is there inside the same device. So the splitting is only for our understanding. So the splitting is not there inside the SCR device. So the SCR is a four terminal single device. Why we are splitting this SCR as a two transistors means we are going to analyze the effect of all the currents using the two transistor model of SCR. So you can see that SCR can be considered to be two transistors NPN and PNP connected back to back. Back to back means the collector of one transistor is given to base of another transistor. The collector of another transistor is given as input to the base of another transistor. So these two transistors, the base and collector terminals are connected back to back. Okay. So now I'm going to write the current equation. So from here I can write IB1 equal to the total current IA is coming. The total current IA is coming, and IA is equal to, you can write the emitter current IE1 equal to IC1 plus IB1, correct? And IE1 is going to be the anode current. The same currents are same. So from that, if I find IB1 equal to IA minus IE1. Okay. See, using the conventional current equation of transistor, right? So IE is equal to IC plus IB. I'm going to use that equation here. Only thing, my IE is going to be my IE is going to be IA. It's the anode current. Okay. So from that, if I find IB is equal to IE minus IC, and IE is going to be IA. So see here, IB1 equal to IA minus IC1, IA minus, in the transistor, I can write IC1 as alpha 1 into IA. So it is 1 minus alpha into IA. So I got the expression for IB1. And IB1 and IC2 are same. So I can write IC2 equal to alpha 2 into IK. From this transistor, you see IC2 equal to alpha 2 into IE2, and IE2 is going to be IK. See, you are writing, see, all the emitter currents are same as the anode and cathode current. So IE1 is equal to IA, IE2 equal to IA. So wherever I have the opportunity to replace the emitter current, I can replace IE1 by IA and IE2 by IK. Now substitute equations 5.2 and 5.3 in 5.1. IB1 equal to IC2. IC2 equal to alpha 2 into IK. So alpha 2 into IK equal to 1 minus alpha 1 into IA. So this term and this term will become same. And you can see from this in any SCR device, the cathode current equal to anode current plus gate current. So this relation is valid for any SCR. So now I'm going to substitute this one again here. So 1 minus alpha 1 into IA equal to alpha 2 into IK. What is IK? IA plus IG. So now take IA terms on one side, IG terms on another side. So 1 minus alpha 1 minus alpha 2 into IA equal to alpha 2 into IG. So what is IA? IA equal to alpha 2 into IG by 1 minus alpha 1 plus alpha 2. So this is the anode current which is flowing through the SCR, which is dependent on the gate current and other parameters alpha 1 and alpha 2 of the two transistors. If alpha 1 plus alpha 2 equal to 1, now we are going to analyze what are the possible conditions for the anode current based on the gate current. See here, if alpha 1 plus alpha 2 equal to 1, then the anode current is infinity, which means the anode current suddenly reaches a very high value approaching infinity. When a very heavy current is going to flow through the device is said to be in on state. So the device will be entering into on state from the off state. So this characteristic of device is called as regenerative action. So when alpha 1 plus alpha 2 is approximately equal to 1, the anode current suddenly approaches infinity. So this turns on the device from the off state, and this characteristic of the device is called as regenerative. Regenerative means it is going back into the active region where it is going to be in on state forever. And the value of alpha 1 plus alpha 2 can be made almost equal to unity by giving proper positive current to the gate for a short duration. So if you give a proper current for the gate for a short duration, you can ensure alpha 1 plus alpha 2 equal to 1, so which will turn on your device. The signal IG applied at the gate, which is the base of T2, will cause a flow of collector current I2, therefore transferring T2 into on state. So now you can see both the transistors are going to be in on state. So when the transistors are in on state, they are in saturation. So very heavy current is going to flow through the collector terminals of both the transistors T1 and T2. So this action is regenerative since each transistor would supply base current to the other. So if you see the diagram, T1 will supply base current to T2. T2 will supply base current to T1. So it is a regenerative action. This keeps on continuing as long as the gate current what you give is sufficient to produce a very high anode current. Regenerative means it is going to happen repeatedly or frequently, or it is going to happen for a longer amount of time until an appropriate current is going to be given. So the action is said to be regenerative since each transistor would supply base current to the other transistor. The one base current is supplied from T1, base current is supplied from T2 collector. T2 base current is supplied from T1 collector. Okay. So at this point, even if your gate is removed, there is no effect on the device. So the device will keep on conducting. So how to turn off your device? So your gate has no role in turning off your device. Your device can be turned off only by reducing the current to a minimum value of current less than the holding current IH. Only when current is less than the holding current IH or voltage is less than the holding voltage VH, the device is said to be turned off. Otherwise, it will be running only in on state continuously. So this is going to be the operation of